This is the second part of the Shorelines lecture. We're going to start with coastal deposition. So we'll talk about a beach. What is a beach? A beach is composed of unconsolidated sediment, and it extends landward from the low tide line until a change in topography, meaning where the dunes begin, or perhaps a cliff, or even a seawall. Okay, so you have your low tide line is approximately over here. And then you have a change in topography. So here are sand dunes, but in some locations, this might be a rocky cliff or a cliff made of clay or something unconsolidated. Okay, but generally this is your beach. The beach is the most actively changing part of the coast. And then we have other terms. The back shore is the area of the beach that's usually dry. The berm is the part of the back shore that's steeply sloped. So it's a little bit steep going down into the water. This will be steep. The beach face is below the berm. It's affected by wave action. And then foreshore is the term for the area that's exposed at low tide, and then during high tide, it's underwater. So here is a diagram from the book. And again, it shows your foreshore. That's also called the intertidal zone because during high tide, it's underwater, and during low tide is exposed. Your back shore, the berm, and here's the sand dunes or the cliffs. Okay, so this area that generally remains dry on the beach is going to usually be where you want to set up your blanket and umbrella or whatever, because it's going to be dry the whole day, rather than somewhere that during high tide, you're going to have to move back. Okay, so a lot of people like to sit back here. Now, what about the sediments on a beach? Quartz is the most common mineral on sandy beaches because it is the most resistant to weathering. You do have other minerals that are found in the sand as well. Magnetite, zircon, garnet, and feldspar. Most sediments on beaches were transported there by streams, and beaches are made up of whatever loose material is available. So some beaches are going to be made of broken seashells, perhaps coral fragments, volcanic rocks, gravel. It just depends on where you are and what loose materials are available. This is some sand. It's a close-up of sand from Orchard Beach in the Bronx. And it's made up not only of quartz, but it's also got magnetite and garnet and feldspar in there. Now, beach sediments that are affected by waves are going to undergo abrasion. They're going to hit into each other, being tossed around in the turbulence of the waves. And then they're also going to have sand grains bump into them as well. So sand grains will bump into pebbles, and the sand grains bump into each other, and everything is bumping into the seashells. And all of this bumping into each other is causing abrasion. So what you end up with is very, very smooth, rounded pebbles. And the seashells are also going to undergo abrasion and be smooth and rounded. So this is a seashell down here. Okay, and this in here is a piece of beach glass. Beach glass is just broken glass that gets caught up in the waves, and then it acts like a sediment as well. so it becomes rounded and smooth. So here's beach glass. Then we have a rack line. This is a rack line. And you'll see this if you go to the beach. When you look, like if you were sitting right here, if you look to the left and you look to the right, you would see a line. Many times it's not this pronounced, but you usually see some sort of line, either a line of broken shells or maybe some marsh grass, maybe some seaweed. So rack lines are linear piles of marine debris. It could be natural and man-made debris. So shells, seaweed, beach glass, sea foam, seagrass, but also just garbage, like random pieces of styrofoam or things like that. And they get washed up onto the beach from incoming waves. And they're oriented parallel to the shoreline, and they tell us how far inland the water came during either a recent storm or high tide. So if you go to the beach after a storm, like a nor'easter or a hurricane, you're gonna have a rack line all the way back. So like after Hurricane Sandy, I went to a local beach and there were rack lines all the way like underneath the boardwalk, like pretty far inland. There were lines of debris, marine debris. So that indicates how far inland the water came. And I have another snip from this Beach, a River of Sand movie that I will show you. So sand on a beach is constantly being moved down the beach by waves, beach drift, and longshore current. So what happens if the transport of sand down the coast is interrupted? So sand on a beach is constantly being replenished by the longshore transport. Okay, so the longshore transport in this diagram is going this way. And they built these groins. Groins are constructed at right angles to the beach, and they're made to interrupt sediment transport and trap the sand, and it allows the beach to become wider. Because the sand, remember we learned the other day, if I can just quickly go back, right? Sand is picked up from here and moved across. So that's how sand is constantly moving down the coast. So you have erosion and deposition constantly happening. So if you interrupt that movement by constructing these groins, it allows the sand to deposit next to the groin, and it makes this beach wider. Okay, so instead of the beach starting back here, you have more beach area. Okay, because it traps the sand. So the sand is moving this way, it's gonna get trapped on this side of the groin. So the movement, and then it gets trapped, okay? So that's interrupting that beach drift. And these are groins along Far Rockaway in New York. And you can see it allows for growth of the beach. Now, the transport moves in this direction. So you have a little bit of erosion on this side, and then the sand is transported this way. and then it gets trapped right here. So you're building this part up. But right over here, you'll have a little bit more of erosion because you're losing that replenishment from this direction. Okay, so each of this side of the groins along this picture experiences erosion, but then it allows the beach to build up. And you can see over here, it's a little bit more significant. A little bit more. See, these are like wide beaches. Okay, so again, groins are built to allow for sand to accumulate in one section of the beach. It interrupts that movement, and then you have sand buildup. Now, jetties are built to prevent deposition in channels. So it allows you to keep an inlet open. They're usually built in pairs. And again, let's say whichever direction longshore transport is in this diagram, let's say it's going this way. The sand is going to build up here and keep this inlet open. So then boats back here are going to be able to still use this channel or this inlet. So then I added a little sand buildup right there. See? Okay, so longshore transport going this way, and then the sand builds up along the jetty instead of going across. If the jetties were not here, the sand would just go across like this and block off that channel, and it would make a continuous sandy beach. This is a jetty at the western point of Breezy Point, New York. And the longshore transport is going this direction. So all of this is sand that builds up along this jetty. And this channel is left open. Then we have something called a breakwater. A breakwater is this dark rectangle here. It's a barrier that's built offshore parallel to the coast. Okay, so here, this is all the beach. The longshore current is moving this way. The point of a breakwater is to create a protected area so that boats can dock behind it and be protected from strong ocean waves. But because you're not having the waves hit the sand, you're disrupting the formation of longshore current. So you're gonna get sand building up behind the breakwater. You get this bulge here. So in order to keep using this breakwater, you'll have to dredge out that sand bulge. Okay, so here's your breakwater, and here is your bulge. So then you have to dredge that sand out in order to still have deep water so that boats can go there. So now we're going to talk about sea level changes. There are two types of sea level change: eustatic and relative. Eustatic is referring to changes in global sea level. That's related to the amount of water in ocean basins, or the volume. Global sea level change is related to warming of the oceans and a change in the amount of water in the oceans. So warming of the oceans, which is related to global climate change as the Earth becomes warmer, that affects sea level because water actually expands as it gets warmer. So the volume of the water increases because it's expanding, because it's getting warmer. That's just a physical process that water expands when it's warmer. Okay, so that itself is increasing ocean volume. That's actually a significant component of sea level rise. Then also, we actually add water to the oceans by having glaciers melt. And then if you have glaciers growing, then you actually have a lower sea level. But in our present day Earth situation, we have glaciers melting. So relative sea level change is local sea level change, and that's related to land uplifting or land subsiding, which is basically land that sinks. So if land becomes uplifted, the sea level is going to appear to drop. If the land is subsiding, your sea level is going to rise. And these changes can be related to plate tectonic activity, glacial isostasy, and sediment compaction. Glacial isostasy, by the way, is referring to when you have glaciers, like the continental ice sheets from the ice ages. Think of like a mile thick block of ice pushing down on the land. So when the glacier melts, the land is able to rise up again. The isostatic rebound of land after the pressure of the glacial ice leaves. The land that was pushed down under the weight of the ice, that land is going to rebound. So that's related to, that's the glacial isostasy. Sediment compaction is referring to sediment becoming more compacted underground, and that's going to lower the land. So the New Jersey coast, actually, the land is subsiding. So sea level rise is about 3 millimeters per year along the New Jersey coast. Now, the global sea level rise is about 1.8 millimeters per year. So the sea level is rising along the New Jersey coast more than it is in many locations around the world. A lot of that has to do with sediment compaction. A lot of the Atlantic coast, a lot of the states along the Atlantic coast are experiencing sediment compaction, which causes the land to subside. You can also have relative sea level change related to plate tectonics. So here, the village of Portage, that is in Alaska, it's now flooded at high tide because of 6 feet of tectonic subsidence related to an earthquake in 1964. And then these trees are in an area which subsided 3 feet during the earthquake, and the subsidence dropped the roots of the trees below the high tide line. And spruce trees do not like salt water, so they died. And then related to sediment compaction, coastal areas with river deltas and also composed of a lot of loose sediment may experience sea level rise faster than anywhere else. So they may even be 9 to 10 millimeters per year of sea level rise. So then here we have global sea level rise might not be so bad in some places where the land is rising because the relative sea level change is counteracting the global sea level change. So you have to add the relative sea level with the global sea level change. And if one of them is negative, in this case, if the land is uplifting, you're getting a drop in relative sea level. So it counteracts the global sea level rise. But we're in areas where land is sinking, then you add the global sea level rise with the relative sea level rise, and you get an increase. So that's why we have the New Jersey coast, because the land is subsiding, along with the global sea level rise, you're getting 3 millimeters per year of sea level rise. So sea level rise threatens beaches where sand in many areas are going to require replenishment to build up the beach again, especially after storms where you have the wind blowing the water onto the coast, which is called storm surge. So you get more flooding, and that erodes a lot of the sediment. So then you have to replenish the sediment on the beach, especially in tourist areas where, you know, for the economy, it's important to have a well-established sandy beach if you're going to have a lot of tourists come. So a lot of money goes into replenishing the sand. Many coastal areas will become flooded as sea level rises further inland. You'll have an increased flooding during storms, and also you'll have saltwater intrusion into coastal groundwater. So as sea level rises, the saltwater gets into the groundwater, and it could turn the groundwater into salty water rather than fresh water. So then I have a quick video on rising sea levels. So here is a picture showing you the sea level rise problem in Miami. And this is not a storm. It's not related to a storm, okay? This is just a regular day, and this is high tide. And this is a problem. And I saw a report that showed by 2050, parts of Miami Beach are going to be under water, perhaps. It was predicting that there would be areas that people would have to move out of, that you wouldn't really be able to live there any longer because of the sea level rise. So this is happening basically now, okay? Sea level rise and the problems that it is related to is happening now. This is not something like, oh, 200 years ago from now, we're gonna have a problem. No, this is now. Okay, Norfolk, Virginia has a significant problem with flooding. And part of the problem is related to sediment compaction. And some of the areas of Norfolk, Virginia are built on what used to be marshland. So you have marshy sediment, like soft peat sediment, like just soft marsh sediment that they built part of the city on. And that sediment gets compacted together. So the loose, unconsolidated sediment under parts of Norfolk, Virginia are undergoing compaction. The land is subsiding, and then that allows the sea to basically flood the city. So this guy here is standing on a flood wall in an area of Norfolk, Virginia that is regularly flooded by high tides. So they have significant problems there. And this shows you a map of sea level rise and how it will affect New York City. So the red indicates land expected to be flooded with 1 meter of sea level rise. That's expected to be by the year 2100. So those are areas that are expected to be flooded. And what they mean is that by the year 2100, the researchers are expecting approximately 1 meter of sea level rise. And again, 1 meter is about 3 feet. The yellow areas indicate land expected to be flooded with 6 meters of sea level rise. And that's a longer time range, not anything specific, just if we were to have 6 meters of sea level rise, the yellow areas would be underwater. And then I have a video to show you about sea level rise in New Jersey. That brings us to the end of the Shorelines lecture.